Bismillahirrahmanirrahim. Greetings. This is going to be the third video lecture that I'm uploading about the concept of composition of functions. Now, I intend to upload one or two more lectures about the chain rule, which is one of the most extensively rule used in differential calculus. The topic belongs to freshman calculus, and that is because the chain rule is based on composition of functions. Now, in this video lecture, I'm going to demonstrate the concept of composition of function through a picture, and also I have made 3D models to demonstrate, and then I will be corresponding that demonstration to an analytical interpretation or mathematical interpretation of that. So seeing is believing, and hopefully by this the concept will be more comprehensible and stays with you for the rest of your life, hopefully. Okay, then let's get started, shall we? Now, before I go to the main body of the lecture, let me say a few words aside. Now, in this video lecture, I'm using, as I already mentioned, three gear trains. And I selected that the radii of them to be in the ratio of 1 to 2 to 3 for simplicity. And then they all are going to rotate about their center, and the first gear, the smallest of the three when you see it later, will be the one that initiates the mechanical rotation. All right. Now, one way that I always apply in my lecture is that to improve the mental picture of the subject, rather than using a 2D picture or a 3D model, is a much better dimension and better for comprehension of that if they can see that. Some it depends of course of the subject. Some subject they do need picture and 3D in order to improve that picture in their mind. But now the demonstration that I make, by the way, if I do it in because I'm facing you, if I do it this way, is less kind of comprehensible than if I be in the same side that you are. So I will rotate myself so that I don't be the mirror image of you, and I demonstrate it that way, if I may. Now, my hand is going to be one of the gear, let's say the smaller one, and the finger of my hand are going to be the teeth of the gear that they engage to one another. All right. Now, let me turn around. Now, when my hand is going to rotate clockwise, you see that the finger of me, that is one of the teeth of the of the gear, will engage with the teeth of the other one, and it pushes downward. You see that? And that causes that the second gear to rotate counterclockwise. Do you see that? So when this is pushing down, it makes it to rotate counterclockwise. Now, let me go now to the picture, and I also have a 3D the model that I have made. The picture, as you notice, as you see it, I have already written that the ratio of the radii of the gears are 1 to 2 to 3 for simplicity. Now, when this gear starts to rotate mechanically about the center, moving, you see the teeth of that is engaging to that one, and you push this one toward going that way, which means counterclockwise. And when this is going counterclockwise, will cause this one to go clockwise. You see that for yourself, huh? Now, this also has a good mechanical engineering application, because if you want as a mechanical engineering, if you want two wheels, two gear trains to rotate same direction, clockwise or counterclockwise, you need to put a third one in between, as the picture indicates. Now, I have made my own also 3D models that I am going to share with you, and as far as the rotation is concerned, so that the seeing is believing. Now let me see. Hopefully it stays. Okay, here these are now. In the demonstration that I'm going to make, this is the one that has the radius of 2, this has the radius of 3, then the smaller one, which initiates the rotation, is going to be here. I will show you soon. So now look at that one. When this is rotating clockwise, you see, when this is rotating clockwise, makes this one to rotate counterclockwise. You see that? And so on. You can see it. So when this is rotating clockwise, this is going to rotate what counterclockwise. See, no? Oh, here it is going like this one. Okay, now, by the way, I use the regular household equipment. Let me show you. I use this one as a circle for the bigger one, and then I use this one to make circle for the second one, and then I use this one to make circle for the smaller of the 3 gears. Now the reason I said that, because just household stuff you can use as a circle to make models you can find for them. But if you have a protractor, it's much better. Also, I'm using cardboard, and if there are things in the I don't know what they call it, foam or something, they are large enough. In the Dollar Tree, you can buy them for $1, and then they are a little bit stronger than cardboard, and depending on the topics, because I have taught math education from kindergarten to 8, and also for high school potential students, and in those classes I always assign as a homework to do as a project homework to make models depending on the topic that I'm lecturing, and of course that will be part of their grade. And if they are living in dormitories that they may not have access to those equipment, I may just do that in the math lab or in a classroom, and bring scissors and protractors, and each of them they start to be active to make models for themselves. To make model is very important, because it stays with them hopefully for the rest of their life, and improves their conceptual understanding of the subject. Now, let me go now to the picture that I draw. This is another one that I made, and it took me about half an hour, not even half an hour, about 20 minutes. About 20 minutes it took me to make this model. So it's not going to take much. Now, when this is the smaller one that initiates the rotation, and all of them are, I already mentioned, they are rotating about their center. When this starts to rotate clockwise, makes this one to rotate counterclockwise, and then this makes this one to rotate clockwise. So as far as the rotation is concerned, you can say this is a function of this, as the literal meaning of the word is concerned, and this is a function of this one. And when we go to composition of function, we see that the middle one will be kind of catalyst. We can filter it out so that this one will be directly a function of this as far as the rotation and number of rotations are concerned. We will see that when we go to mathematical interpretation. So here, you see that when I rotate this one clockwise, you see that when it's going, this one is going, well, let's put this way. When this goes counterclockwise, this is going clockwise, and this is going clockwise. You can see that, huh? Look at that. You see that? Is that the teeth are not strong enough to hold themselves, and I'm sorry for that. Here it is. It's going now. You see that? Now this one is going counterclockwise. And if I go this way, this one is going clockwise, and this one is going clockwise. Okay, now now let me go to oh, by the way, let me say one more thing about this subject. When this a small one is rotating one time, one complete rotation, 360 degrees, that will make this one to go half a rotation, 180 degrees. Why? Because the radius of that is twice the radius. The ratio of the radius of this to this is 1 to 2. Oh, I already mentioned that. And so when this one goes one complete rotation, the small one, makes this one to go 1/3, because the radius of that one is 3 with respect to this one. Do you follow me? So when this one is turning 2 complete rotation, this will turn this will turn how many? 1 complete rotation, and this one will turn 2/3 of a complete rotation. Do you follow me? Again, as far as the rotation is concerned, this is a function of this, and this is a function of this. Then we go to the mathematical interpretation so that this becomes a function of this. This will be a catalyst, and we can filter it away, in a sense. Do you follow me? Now, the other thing to say is that if you want this to be the whole number, not 1/2 and 2/3, to be the whole number, so we go to the least common multiple of 2 and 3, which is 6. So we go with multiples of 6, then the rotation of these wheels will be a whole numbers. I come to that when we go to mathematical interpretation. Okay, now I guess we are ready after that to go to mathematical, analytical interpretation, in a sense. I read it for you what I have written, in case, some students, they like to take notes. Now, here, once gear A takes T turn, now we are working with the number of turns, which is a number. Gear B, the middle one, will take X turns, all right? And then gear C will take Y turns. Now we want to relate T to X and Y, all right? We want to relate T, X, and Y together. Now let's see how I do that. Now here I have written, and I think it's large enough, I don't need to zoom it. T is going to be a positive number. As a positive number, positive real number. Does not have to be a fraction, does not have to be a whole number. Now, T, in this case, in our demonstration, is number of turns of the what of the in the smaller, the one that initiates the rotation. So t is number of turns of that. Then the second gear, as you notice, is a function of the first with respect to the rotation. So b of t, how many times that will rotate? Let's say that to be x, and that x will be called 1/2 of t. I went over that. Now, for instance, if t is 1, which means the smaller gear, it rotates only once, one complete rotation, this will make half. You see that? Makes half. If it rotates t, number of rotation, if this makes 2 complete rotation, will cause that one to what? To rotate 2 is 1 complete rotation. All right? Now, the same is true with the what? With the C one. Let me go also over that. In the C case, now C, as far as the rotation is concerned, is a function of this wheel, of this gear. So when this rotates 2 times, this rotates 1 time, and this rotates 2/3 of a time. Now, in order to make it a whole number, not to work with fraction, we can take the least common multiple of 2 and 3, which is 6, and then go with the multiples of 6. I have written them, I will go over them for you. So when this one makes a 6 complete rotation, will cause the middle one, this one, to rotate 3 complete rotation. And when this one makes 3 complete rotation, makes the larger one 2 complete rotation, because of the ratio of what? Of the radii that I have already mentioned. All right, then, are you comfortable with that? Now look at this one. C now is a function of b, and b is a function of t. Do you see that? So C is independently by itself is a function of x, and that is 2/3 of x, and x is what? Number of turns of the middle gear, not the first middle gear. So I have written t, and b is a function of t, and c is a function of b. Is that right? And then when you do simple arithmetic addition or division, you will come back when we put for x 1/2 of t, when you replace x with 1/2 of t, then what happens? 2 and 2 they cancel, so you are left with 1/3 of t. And that is correct. So when t is 1, for example, the middle one will turn half, and the last one on the right, the larger of the 3, will make 1/3 of a turn. And if t is what? Is a multiple of 6, we will have whole number of rotation. You know, this has a lot of good mechanical application. For instance, if you are familiar with the car, when you turn the starter gear goes to flywheel, you know, and the teeth of that, they start to rotate that one. So the flywheel start to rotate, and that causes the camshaft to move, and that piston goes up and down, and the car starts. And also, as far as the whole number is concerned, the mechanical engineer, they make the radii of the gears accordingly, so that the turn of them will be a whole term. All right, is a multiple of whatever the radii are. So that will have, and that also has effect, simplifies and helps for the car mechanic, so that they have mark on the, for example, timing chain. They have kind of a mark, and those marks they will align so that they know they can put the chain or the timing belt or something back and that. If you are familiar with the mechanical work of car, which is kind of elementary, you know exactly what I'm talking about. All right? Okay. Now let me go to another one if I may. Now here for what I have already mentioned, I'm going to that one more time. It's kind of important. And that is here, for a complete rotation of each gear, we let t to be a multiple of 6, where k, I wrote 6k, where k is a positive integer. We don't have to say a whole number, which includes 0, and 0 is trivial. When it is 0, that means there is no, rotation has not happened. There is no rotation. Okay, so this is clear. Now, when t is 6k, when k now takes over, when k is 1, t is 6. When k is 2, t is 12. When k is 3, t is 18, and so on and so forth. And 6 will be the least common multiple of 2 and 3. You with me? Now, b is a function of t. Now, instead of t, I write 6k. You see that? So I write it in terms of k. So when I do that, then x will become what? When I simplify, x ends up to be 3k. Do you follow? And the same is true with the larger one of the 3 gears. And c is a function of b, and will be c of x, will be c of b of 6k. And again, when you make arithmetic simplification, 6 and 3 goes to 2 is 2k. Now you can see that for yourself. When k, for example, is 1, look at that, the c will make a 2 complete rotation. And when k is 1, the middle one, the b gear, makes 3 complete rotation. And when k is 1, look at that, t will be 6, which means the smaller one is rotating 6 complete rotation. You follow me so far? Okay, now let me go to the function notation of that and relate that one to the composition of functions, if I may. Now, in the previous lecture, I've gone in more detail about the notation, and I mentioned that this notation is a suggestive notation in a sense that contributes to the concept. So x is assuming its values from the domain. And then f of x is the image of x, which means what is going to be paired with x. And what is going to be paired with x, it is f that determines that one. What is going to be with. Now, this notation makes the comprehension of composition of function much, much easier. It's a suggestive notation. Now, here, look at what happens. The x is in the domain of f, but that image of that must land in the domain of g in order for g to function. You see that? So, and in the demonstration that we made, b, the second one, the second gear was a function of t, and t is the number of turns of the first gear, and then c is a function of the middle one. So now when we compose them together, then c, the composition function, becomes a function of the first gear, which means the third gear becomes a function of the first gear, and the second gear will be kind of catalyst. It goes kind of can be filtered away. You follow me? It's very beautiful. Okay, now let me go to a schematic diagram to make it a bit more kind of comprehensible. Now, again, I have looked at them. I don't think I need to zoom it up, but I will go over that. And from my work, you can also see what I'm saying. Now here, this ellipse is full of positive real numbers. It's full of positive real numbers. So I select one of them as a typical representation. So B, and that T is the number of terms, so it does not have to be whole number. Can be any real, positive real number. Now, then B of T will be 1/2 of T because of the what? Of the ratio of 1 to 2 radii. The second one is a larger radii. And then the image of this will be 1/2 of T, which is X. Is that right? Now, the domain of the C, gear, the domain of that is also all positive real numbers. So this is positive real number, this is positive real number. When they superimpose on the top of each other, which means the range of that superimposed on the top of the domain of the C, so that because in a true sense will be a improper subset of that, which means completely covers that, because this one is also, X is also all positive real numbers. Then we can go directly from T to the C. The rotation of that goes from a smaller gear to the larger gear directly. Now, let me see what, when I combine them, how it will. Now here I am combining the two, the range of the B on the top of the domain of what? Of C. And you see that? Now, F, and I have used it F because in the previous lecture I used function notation F and G, so I have also used F. So F of T, now T is a real number, will be 1/2 of T, and then G takes over that 1/2 T, the image of that, G will take, because lands in the domain of that, and it will give you 1/3 of T. I've gone over that, Now we can go directly from T to what? To the C of B of T, which is composition of the function. So C circle B of T is C of B of T, which is 2/3 of 1/2 of T, and 2 and 2 they cancel, become 1/3 of T. You see that, Now, I don't have anything else to demonstrate here. Now, this concept is, I'm sorry, I know that I don't have a microphone so that I can filter out the echo. I have noticed that in some of my video lecture there are some echo. But hopefully it's clear to you, and also my recommendation to you is every of them that you're not too comfortable, fortunately you have upper hand, you're using computer, try to pause, think, reflect, make sure you comprehended that very well, and then continue. If it is in live class, I will stop. I will make sure that they have comprehended the idea, the students, before I continue and go further. But here I'm continuously doing that because of the technology of the computer. You can pause it for yourself. Okay, then I thank you for watching, and as always I wish you prosperity and good health, and please stay safe. So long.